Hello, everyone. Today I'm going to talk about hypergeometric distribution. Sometimes I call it a good potato, bad potato model. Why do we study this kind of model? It's very useful in quality control. So here is a simple example. I'm going to solve this a little bit later after we introduce the model. Say, suppose that you run a small family store that sells smartphone covers. And one day you receive a shipment of 1,000 covers from a factory. The factory claims that there are only 5 of them that are defective, and you feel dubious. However, it's time-consuming and very expensive to check all 1,000 covers. So instead, you check 10 of them and find one defective cover. So what are you going to say to the factory? Are you going to believe the factory's claim or not? Well, I mean, it's possible, right? If you say to the factory, say, "Oh, why do you have why I have found one defective cover?" He would claim it's possible. So it's important to find the probability, and if it's really small, then it seems to be unlikely to happen if the factory's claim is true. It involves some kind of idea of hypothesis testing. And I will talk about that as well a little bit later. So the key is to figure out the probability. All right, the model and the distribution. What is the distribution? Let me set up the problem using some kind of language. Good potato, bad potato. Suppose we have a bag. The bag has a capital N potatoes, in which capital G are good and capital B are bad. So you add them up, you get the total number of potatoes. And a sample of a little n potatoes is selected at random without replacement. Okay, here it's without replacement. And then we care about the number of bad potatoes. Say, it doesn't really matter. You care about the good potato, bad potato, it doesn't really matter. So let's define X to be the number of bad potatoes. The number of bad potatoes in the sample. Okay. So we are looking for the probability of X equaling K. K is the number of bad potatoes in the sample. And K runs from 0. It's possible you have no bad potatoes. And it could possibly 1 and so forth. And the last number should be the smaller number of capital B and little n. Okay, so this notation means it's the smaller. We choose the smaller of these two because if you cannot have more than the sample size, and you cannot have more than the total number of bad potatoes. Okay, so you have a smaller number, the minimum. It's the minimum of B and N. So this notation means that. Okay, so we use the counting argument or counting technique. The total number of samples without any restriction, it's capital N, choose little n. The number of samples that have K bad potatoes would be you select K from capital B, and then the others are good ones. You can write capital G or capital N minus B, doesn't really matter. There are a couple of things I want to talk about. First of all these combinations do not involve something like that. okay? We are not selecting potatoes from the sample. You select sample from capital N potatoes, okay? So little n should not be on the top of this combination. Okay, this is one thing. Second, it's very easy to forget the second part. I have seen many people just don't have this part in their numerators. The reason is that once we say we select K bad potatoes, we have to select N, not just K. So once you have K potatoes, it's not done yet, right? Because we select N potatoes, so we have to select N of them. Once you select K, possibly there are N minus K left. If N is greater than K. Okay, so you need to have that this term. And the one feature about this fraction is that you add up these two numbers, you will always get this number. And if you add these two numbers, then you would get this number. Yeah, this is kind of a feature of this fraction. So if you see that, if you remember that, it's less likely to make mistakes. All right. So that's the PMF, probability mass function of this model. Now, how can we find the mean and the variance? We can use the definition to figure out the mean. So the mean E of x would be the sum of K times capital B choose little k and capital N minus B over little n minus k, and then capital N choose little n, and k runs from 0 to capital B and smaller number of B and N. It's not really straightforward or very simple to calculate it. Instead, I'm gonna use a slight different way, quite different way. I'm going to express x as the sum of little n random variables. This represents the first potato. And if it's a bad potato, I'm gonna just make it 1. So x1 equals 1 if the first potato is bad. Okay, I have a bad potato. And I denoted 0, I defined to be 0 if it's a good potato. So it is a Bernoulli. Okay, so so I define x2 and xn similarly. So each one is a Bernoulli random variable. We can show that these random variables have the same distribution. So they're identically distributed. However, they're not independent. For example, if the first potato is bad, then the probability the second potato is bad, it probably would be it would depend on the first one. Okay, probably smaller. So they're not independent. But in terms of expectations, that's no problem. We can add, because the expectation of x would be simply the sum of the expectations. And I said that they have the same distribution. So I'm going to just do the product n times the expectation of the first random variable, which is by Bernoulli, right? So let's figure out the distribution of x1. It has 1, 0. So what is the probability that the first potato is selected and it's a bad potato. And the probability would be capital B out of total N. And then this one would be N minus B or capital G over capital N. And we know that expectation of a Bernoulli is simply the probability of X taking value 1. So it's just B over N. So we have N times capital B over capital N. So this is the mean. And the variance, we're not going to prove it. Okay, I'll just tell you what the variance is. The variance of X equals N times capital B over capital N times capital N minus capital B over capital N times capital N minus little n over capital N minus 1. If you're familiar with the binomial distribution, and then you probably would notice that this thing is NPQ, N times P times Q. So it's a variance of a binomial. And this part really tells us sort of quantize the dependence of these random variables x1, x2, xn. Okay, so this is the correction of the variance from binomial. And I will talk a little bit about the relation between binomial and hypergeometric distribution a little bit later. All right, so these are the mean and variance of the distribution. But let's have a look at an example. Now let's go back to the motivation problem. Okay, so we have a total of 1,000 covers. So capital N equals 1,000. Let's focus on defective 1. So capital B, bad, or defective D, it doesn't really matter. I'm going to just use capital B. 5 of them are bad. So there are 995 good ones. And the sample size is N, is 10. You select, you check 10 of them. So little n equals 10. Okay, so we're looking for the probability of you have one defective cover. But actually we're doing something, we are looking for the probability which is slightly different from just one. It has something to do with the concept of hypothesis testing. So the idea is this. Without you checking 10 of them, you have to sort of believing that the factory is not lying. Okay, so that's the status quo. And in hypothesis testing, we're gonna just put it as the null hypothesis. Null hypothesis. So here, the null hypothesis is that the factory is not lying. The factory is not lying. Equivalent to saying that there are only five bad ones. Bad ones in 1,000 covers. And its alternative hypothesis would be that the factory is lying. And the lying means mostly on the common sense that probably there are more than 5. Less than 5 is good, so you don't really want to argue with the factory, say, oh, you're lying because there are only 4 bad ones. You're not going to do that. So the alternative is actually there are more than 5 bad ones, bad covers or defective covers. We're looking for the probability. So this is usually called a p-value. P-value. It's defined to be the probability that you will see those events that are at least as extreme as observed. This sentence is a little bit hard to understand. Given that HO is true, assuming the factor is not lying, that's the status quo, HO. Based on that, we're looking for the probability that the events that are at least as extreme as observed. Observed here, you have one. You found one defective, so that's one defective, one bad cover. Okay. Now, what does extreme means as extreme as? So extreme is to be convincing that the factor is lying. So it's against HO. So if some events that's, for example, you see in 10 covers you select, you found 5, that's kind of extreme because it really against the factory's claim. So extreme is against the HO, it's against HO. Use the at least as extreme as observed. So you observed one defective, and the 2 defective ones would also be extreme, okay, more extreme than 1, so at least as extreme as 1 defective. So 2, 3, 4, 5, all these will be considered as extreme events. They against HO, okay. So what it really means is that we're looking for the number of bad covers. So the events, it means let's say X, the number of bad covers in the sample, X greater than or equal to 1, H given HO. That's what we're looking for. If this probability is small, then we would say, okay, it's unlikely to happen that X greater than or equal to 1 if the factor is not lying. But you actually observed it, right? Because you saw one defective cover, then you probably would argue that the factor is lying. But we need this probability. Now we can use the model to find the probability. X greater than or equal to 0, X greater than or equal to 1, it's easy to use the complement rule. Greater than or equal to 1, the opposite here, 0. That means all are good. So you're going to select 0 from bad ones, totally of 5. And then you are selecting 10 from all the good ones. So that's the numerator. And denominator, 1000, choose 10. Okay. We calculated it. It's 1 minus 0.9509, and then we get 0.0411. So now the question is this probability small or not? Usually, there's a benchmark to determine that. In statistics, we call it the level of significance. It depends on you two people, you and the factory. Usually, you determine or you agree with a certain number. But in practice, people usually use 0.05 as the benchmark, the level of significance. So if you choose this number to be the number, whether you determine it's small or not, right? Then 0.0411 is less than 0.05, and you would claim that it's unlikely that you will see at least one defective covers in the sample if the factory is not lying, but you saw it. So it's likely that the factory is lying. All right. And in statistic language, we're going to simply say, oh, HO is rejected. there's a statistical evidence that the factory is lying. And how to deal with that? Maybe the shipment will be returned. All right. So this is a simple example of the application. It can be used to used in quality control. For example, the factory makes a lot of products, and there's no way you're going to check all of them, or obviously it's not realistic. So usually you take a sample of the products and see how many are good, how many are defective. Other than you can get some idea about the whole population, the whole all products. All right, so this is one example. Let's look at another example. This example is not practical, but it's kind of using toy models. I like using this kind of problems to give examples. The box has 40 black balls and 60 white balls. A sample of 10 balls is selected at random without replacement. Find the probability that there are 4 black balls in the sample. Okay, so here we have capital N, you have 100. Which one is bad, which one's good? It doesn't really matter. Okay, it doesn't really matter. You can say capital B to be, but here's black, not bad, 40. And W to be 60. All right, and the sample size is 10. And you have 4 black balls. You choose 4 from 40. Don't forget the second term. You're gonna choose 6. It's a little n. 10 minus 4, 6. You choose from 60. By the way, it's a combination. Okay, this notation is combination. Some people use C, 40, choose 4. It's the same thing. Both are commonly used. But I'm gonna just use 100, choose 10. Okay, these numbers are a little bit big. 100, choose 10. I don't want to calculate it. I want to just leave it like that. Next one, there are at least 1 black balls in the sample. So at least 1, you could have 1 or 2 or 3, or at least 1 is greater than or equal to 1. So you could write 40, choose 1, and 60, choose 9, and then you have a 100. Let's put 100 over 10, the bottom. And then you have a 40, choose 2. That's really tedious to calculate. Some people just write ... and leave it like that. It's not wrong, but it would be preferable using a different way, which is using the complement rule. So let X be the number of black balls. And we're looking for the probability of X greater than or equal to 1. And using the complement rule, is 1 minus X equaling 0. So it would be 1 minus 40, choose 0, it's simply 1. So we can just write that. It doesn't really matter. If you insist on putting 40, choose 0, that's no problem. Then you do see 40 plus 60, 100, 10 plus 0 is 10. But this number is 1, so really it doesn't really matter. Okay, so this is at least 1. The next one, there are at most 2 black balls in the sample. At most 2 is less than or equal to 2. I always tell my students that whenever you see at least, at most, you should think about the complement rule, but it's not guaranteed to use. You still need to analyze the event itself. So here at most 2, 0, 1, 2. It's not that bad. And the complement would involve 3, 4, 5 to 10. It's more complicated. So for this one, it's really, you don't need to use the complement rule. So it would be just what? 0. 0 black balls, all white, 60 choose 10. And then you have a 40 choose 1, and 60 choose 9, and then you have 40 choose 2, and 60 choose 8, and the bottom is the same, which is 100 choose 10. All right, so this is a problem that shows using at least at most this kind of thing. Okay, oftentimes you will see this kind of language in this type of problems. The next problem is a little bit complicated. In 130, we don't do this kind of problem. In 255, maybe. So let's do that. A purchase of electrical components buys them in lots of size 10. So each lot has size 10. It is his policy to inspect 3 components randomly from a lot and to accept the lot only if all 3 are non-defective. If 30% of the lots have 4 defective components and 70% have only 1, what proportion of lots does the purchaser reject? Reject, that means you find some defective ones. Okay. All right, so it's a little bit complicated. You have 2 types of lots. Let's draw a tree diagram just to show the situation. It's not necessary, but maybe it's helpful. The first type, lot type 1, lot type 2. 30% of the lots have 4 defectives. So lot 1 has 4 defectives. Let's put 0.3 here, 0.7. And in lot 1, you have 4 defectives. So 4 defective, let's put D. And lot size 10 is 6 non-defective. And in the second type of lots, there's only 1 defective and 9 non-defective. Here, these numbers are not a conditional probability. Okay, they are the counts. They're not probabilities. So that's something try to take notice that. All right, now let's calculate the probability that all are good. All are good. In the lot, lot type 1, you have 4 good ones, 4 bad ones, and 6 good ones. Total you have 10. And you select 3 of them. Okay, so capital N is 10, and you select 3 of them. So all right, so in the first type of lots, let's figure out the probability that all 3 are non-defective. So accepting, yes, accepting it. So you would have at the bottom, lot size 10, you choose 3, and all 3 are good, so 0 from bad ones. You have 4 defectives, and then you have 6 good ones. You can choose all 3 from those 6 good ones. And for lot type 2, you have a 10 choose 3 on the bottom. And numerator, you have 1, choose 0. And then you have a 9, choose 3. All right. So these are based on those probabilities. You need to multiply these probabilities. And this is actually conditional probability. This is conditioning on the first type. So like Bayes' problem, you can actually multiply these probabilities. You have 6, choose 3. Let's forget about 4, choose 0. Okay, 10, choose 3 times 0.3 plus 9, choose 3 divided by 10, choose 3 times 0.7. Now let's calculate it out. The numbers are not that big, so we can do that. 6, choose 3 is 6 times 5 times 4 divided by 3 factorial. But then the bottom also has the 3 factorial. So we're going to simply do that. 10 times 9 times 8 divided by 3 factorial, but 3 factorial will be canceled out. And similarly, you have a 9 times 8 times 7 divided by 10 times 9 times 8 multiplied by 3 does 0.7. Okay, so we calculated. Okay, so you have a 20, you have 2, and then you have a 1272, 1/6 times 0.3 plus, that's kind of easy, 0.7 times 0.7. So we have this is 0.1 over 2, 0.05 plus 0.49, you get 0.54. This is the probability of accepting the purchase. Okay, so the answer for the problem is 1 minus 0.54, 0.46. So that's the answer. All right, so that's this problem. I wanted to talk a little bit about the relationship between hypergeometric and binomial models. So hypergeometric, you have capital N potatoes, and some G are good, B are bad, and you select N potatoes, and K is the number of bad potatoes. It doesn't really matter, but let's just hit bad potatoes. K is the number of bad potatoes. The key is that we're selecting without replacement. So that's the key. Now, if we're selecting with replacement, you select Y, record it, and then put it back, then the situation becomes exactly the same as before. And then we actually have a binomial because now you have independent Bernoulli trials. For hypergeometric, you have a Bernoulli trials in normal sense, okay, not in mathematical sense. In normal sense, it's just a bunch of Bernoulli trials, but they are not independent, right? In probability, when we talk about Bernoulli trials, we require them to be independent. So, but if it's with replacement, then it becomes binomial. And we would have a binomial, and you have little n to be the total number of trials, which is the sample size and probability of success. If we consider picking a bad potato to be success, you would have capital B over capital N as the probability of success. Okay, so this is one relation. Without replacement, you have a hypergeometric. With replacement, you have a binomial. Now, in reality, sometimes it happens that when the sample size is really small compared with the population, then the hypergeometric model is very close to binomial model. For example, in reality, say you do a survey. You select 1,000 people from, say, 1 million or 2 million American voters, a lot of people. Then, even though you are selecting without replacement, you're not going to select the same person in your survey, right? So it's actually selection without replacement. But because the sample size 1,000 is so small compared with the population size, capital N, then we can show actually the two distributions are very close. One little thing from the variance, you can see that. So for binomial, still using the setting with replacement, you have a binomial, you have a little n and a capital B over capital N, right? It's probably a success. And here, the variance for binomials NPQ, so you have B over N times B over N times N minus B over capital N, that's it, it's NPQ. But for hypergeometric, you have N times B over N times capital N minus B over capital N times an error term, or it's a correction term. And when this N is really small compared with capital N, then this ratio is really close to 1. All right, that shows some evidence that hypergeometry is close to binomial.